Good evening. Okay, so we were discussing about D and F block elements, right? So already we have completed the important part, okay, from D block element. All the properties we have already covered. So last class we were discussing about the magnetic moment also. So we have seen how to calculate the magnetic moments also. So you know the magnetic property also, what is diamagnetic behavior, what is paramagnetic behavior, how to calculate the magnetic moments, right? So last class we were discussing about some of the important compounds of this transition elements. So we'll start with this again. Okay, so there are three important compounds which we'll be studying. So we'll start it with this first. So the first compound which we are going to study is about potassium dichromate. Okay, so what is potassium dichromate? It is K2Cr2O7. Okay, so can you tell me what is the oxidation state of Cr here? What is the oxidation state of Cr in K2Cr2O7? Yes, anyone? There are four: Jyoti, Komal, Nagini, and Priyanka. Yes, anybody can tell me what is the oxidation state of Cr? Okay, Cr is chromium. Yes, somebody has answered. Okay, Jyoti has answered it as 6. Okay, others? So you have already studied about finding the oxidation state in your first year, right? In which chapter? It is redox reaction chapter, right? So once again, I'll just tell you. So you know few elements, their oxidation state, right? Oxygen, the most common. You know the alkali elements, they exhibit +1 state. Alkaline earth metals +2 state. Okay. Then the halogens, halides, right? They give -1. So fluoride, that is fluoride, bromide, chloride. So all are -1. Komal has answered it as -2 or +6. Okay, then so here oxygen, so oxygen will be -2. So commonly it exhibits as -2, hydrogen +1, right? So these are some of the what you say commonly shown oxidation state. Now, potassium is what? Potassium is alkali metal, so it will exhibit as +1 state. So I'll just show you how to solve this now. So here, what is this? K2Cr2O7. K2. Okay, that is potassium +1. So I'll take +1 into 2. Right, +1 into 2, or else I'll not put any bracket. Again, it will be confusing. So here, so +1 into 2 plus. So we don't know. We want to find out for chromium, Cr. Okay, chromium is Cr. So Cr, so what I'll do, it is 2. So 2 chromiums are there. So what I'll do as 2x. I'll put it as 2x plus how many oxygens are there? 7 oxygens are there. 7 into, okay. How many each oxygen is? -2 will be equal to 0. So this is the equation. Now solve this. Now solve it and see what you're getting. So +1 into 2, it will be 2 plus 2x. Okay. Then 7 2s are 14. So this will be -14 equals to 0. Right. Then 2x minus -14 and +2. So this will be -12 equals to 0. So 2x is equals to 12. X is equals to 12 by 2. So 2 ones are 2, 6 are. So each chromium is what? Each chromium is 6. Okay, so each chromium will be 6. The oxidation state is +6. Understood? Okay, so potassium dichromate. So we are going to synthesize, okay, we are going to prepare this compound from its ore. So which are the two ores? So either you can take as ferrochrome. Okay, ferrochrome. What is ferrochrome? It is FeO dot Cr2O3. Okay, or chromate ore. Okay, chromate ore, that is FeCr2O4. Okay, so this is chromate ore. So these are the ores from which your potassium dichromate can be synthesized. So what is the preparation? So the first chromite ore. Okay, so here what is taken? Ferrochrome is taken. So the ferrochrome, what is done? So ferrochrome is treated with sodium carbonate. It is fused with sodium carbonate or potassium carbonate. You can either take K2Cr2O3 also. Okay, K2CO3, potassium carbonate, or you can fuse it with what? Sodium carbonate in excess of oxygen. So what is taken here? It is treated with excess of oxygen to give you what? To give you sodium chromate. So this is what? It is sodium chromate. This is sodium chromate. Okay, plus 2Fe2O3 plus 8 carbon dioxide. So this is a yellow color solution. So here what you obtain? You obtained a yellow color solution. Why? Because of the presence of sodium chromate. Because of the presence of sodium chromate, it converts, you have converted the ferrochrome into sodium chromate. So thus the solution turns into yellow color. So here what happens now in the second step? The ferrochrome, okay, that is the sodium chromate which is obtained. This is treated with acidified, okay, it is acidified with concentrated sulfuric acid to get what? To get sodium chromate. In sodium chromate, what is the oxidation state of chromium? Each sodium is plus 2. Okay, each sodium is plus 1. So there are 2. So it will be plus 2 plus 2x plus 7 into minus 2 equals to 0. So plus 2 plus 2x minus 14 equals to 0. So 2x minus 12 equals to 0. So x is equals to 6. So here also in sodium chromate, what it is? It is plus 6. Okay. Chromium is plus 6. And this turns, so when you are acidifying the sodium chromate with excess of sulfuric acid, it is converted, the sodium chromate solution which is obtained is converted to, it is converted to what? It is converted to a orange color solution. So in the first step, because of the presence of sodium chromate, the solution turns yellow color. In second step, when you are acidifying the sodium chromate solution, it is converted into orange color. Okay. So what is obtained is sodium dichromate is obtained. So in the second step, what is obtained? Sodium chromate is converted into dichromate. Okay. Chromate. So the orange yellow color solution is converted into yellow color. Okay, now next step is what? The sodium solution here. Okay, the solution obtained in the second step is concentrated to get crystals. What is done? The solution of sodium dichromate is concentrated. It is continuous, heated. And what is happening? It has been converted into crystals of sodium dichromate. Okay, thus the crystals of sodium dichromate is obtained. Now in the third step, the sodium dichromate. Okay, the sodium dichromate is treated with potassium chloride. You can see here what is done here. The sodium dichromate is treated with potassium dichromate. Okay, potassium chloride. And what is obtained? Sodium potassium dichromate is obtained. That what is happening? A replacement reaction is taking place. Okay, your sodium ions are getting replaced with potassium ions, right? So what is happening? So sodium dichromate crystals which are obtained, it is treated with potassium chloride. Thus, the potassium chloride, potassium ions are replaced, they replace the sodium ions. And thus what is obtained is, so potassium dichromate is obtained. So this is a preparation of potassium dichromate. So on cooling, so what you have to do, the solution which is obtained on cooling, okay, the orange crystals of potassium dichromate will separate out. So because you're continuously heating, right? So after cooling, what will happen? The potassium dichromate crystals, which are orange in color, they will get separated, right? So this is about potassium dichromate. Now, what about the property? So potassium dichromate is used as a standard solution. Okay, standard solution. Why it is used as standard solution? Because it has a perfect orange dark color. Okay, So it is used in volumetric estimation. What do you mean by volumetric analysis? Volumetric analysis means what? Certain amount of solution, okay, a certain amount of solute, you can say, it is dissolved, okay, and so after analysis means what? You have to perform some set of experiment, and by that set of experiment, at the final, you are supposed to find out how much amount of that particular solute was dissolved, okay, in a particular volumetric flask. So this is the so sodium dichromate as potassium dichromate, sorry, as it has a perfect orange color, it can be used as a primary standard solution in volumetric analysis. So this is the first property of potassium dichromate. Okay. Then the next is what? It is used, okay, it is used in the oxidation reactions. So this potassium dichromate, it is used in oxidation reaction. So in acidic solution, it acts as strong oxidizing agent. So potassium dichromate, it is a strong oxidizing agent. So these are said to be good oxidizing agent. Then you can see the chromate ions, right? So what is done in the second step? You have seen that the chromate ions are converted into dichromate ions. How it is converted into dichromate ions? By acidifying it. Okay, by acidifying it means what? When you are treating it with excess of sulfuric acid, what is happening? Your dichromate, right? The yellow color solution, which was of sodium chromate, is converted into what? Sodium dichromate, right? So we are converting the chromate ions into dichromate ions. How? By acidifying the solution. By acidifying the solution. So again, if you want to convert from dichromate to chromate, how you will convert it from dichromate to chromate? By adding basic solution. Suppose chromate, okay, chromate to dichromate. How we have converted chromate to dichromate? By acidifying the solution. Now, if I want to convert from dichromate to chromate, then what I will do? I will add basic, okay, basic solution. I will add acid. You can read out this second point. So chromates and dichromates are interconvertible. Okay, they can be interconvertible in aqueous solution depending upon the pH of the solution. So if you want to convert chromate to dichromate, I have to acidify the solution. If I want to convert the dichromates to chromate, then what I have to do? I have to basify the solution. Okay, so these are the properties you can say of your dichromate. Okay, potassium dichromate solution. Understood? Okay, so these are some of the properties. Okay, then next we'll see the structure. So what is the structure of chromate ion and dichromate ion? So chromate ion, the structure is CrO, okay, oxygen, 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 and 2 minus, right? So it is Na2CrO4, right? Na2CrO4. So if I remove this Na2, so it becomes CrO4 minus 2, right? So CrO, this O4 oxygen, and this is minus 2. So this is a chromate ion. So this is a chromate ion. So it has a tetrahedral shape. You can see it has a tetrahedral shape, right? Then we will see for dichromate. What is the structure for dichromate now? Dichromate, it will be Cr, O, O, O. Then here one bridged. Okay. Then O, oxygen, oxygen, oxygen. So dichromate is what? Cr2. Cr2, right? Cr2, then O7, 1, 2, 3, 4, 5, 6, 7. Cr2, O7 minus 2. So Cr2, O7 minus 2. So this is the what? So this is the structure of dichromate ion. So this is a structure of what? Dichromate ion. Okay, dichromate ion. Understood? So these are two important structure of chromate and dichromate. So in the first step, after fusing it with sodium carbonate and with excess of oxygen, the ferrochrome is converted into yellow color solution of sodium chromate ions. Now this sodium chromate, what is done? We have acidifying the solution with excess of sulfuric acid. We have treated it. and we are continuously heating it till you get a orange color crystals of sodium chromate, dichromate. Now this sodium dichromate solution, what we have done, we want to convert it into potassium dichromate. So we have treated it with potassium chloride solution. So what is done? The sodium ions are converted to potassium. So we obtain potassium dichromate. So potassium dichromate on cooling, it will give you orange color crystals. So based upon the pH, the solutions can be interconvertible. Okay. So these are some of the important points of potassium dichromate. Okay. So we have seen the preparation, we have seen the properties, we have seen the structure. Okay. So the chromate ion, you can see structure also. The chromate ion, it is tetrahedral. Okay. And dichromate structure, you can see there are two tetrahedron. It consists of two tetrahedra sharing one corner. Okay. So it is sharing one corner with CRO, right? So it is sharing one corner with CRO, and it is making an angle of 126 degree. Okay. So this is about the first important compound of transition element, that is potassium dichromate. Clear till here? Any doubts? Any doubts about potassium dichromate? Okay. So it is clear. Okay. So we'll go for the next one. So next compound is potassium permanganate. Okay. So the next compound which we are going to study is potassium permanganate. So potassium permanganate, it is prepared by fusion of MnO2. What is MnO2? MnO2 is pyrolusite. Okay. MnO2. So what we are going to do? We are going to take the ore as pyrolusite. So it is a ore, pyrolusite ore, which is MnO2. So it is prepared by fusion of MnO2 with KOH. What is KOH? KOH is potassium hydroxide, or you can take NaOH. So either you can take potassium hydroxide or you can take NaOH. So you are going to fuse. You're going to fuse your MnO2, that is pyrolusite, with a base, either potassium hydroxide or sodium hydroxide. Okay, and an oxidizing agent. So oxidizing agent, what it will do, either you can make use of air, okay, continuous air, or KNO3, okay, potassium nitrate solution. So either you can make use of any of this. Either you can use air or any oxidizing agent. So what is done? So after fusing your pyrolusite with base like NaOH and with excess of oxidizing agent or excess of air, you can take. Here they have taken excess of air. Excess of air means what? It is acting as an oxidizing agent. It is providing oxygens. So it is converted into a dark green color K2MnO4. Okay, it gives you K2MnO4. So it gives you a dark green color, which is of K2MnO4, which disproportionates in acidic medium. So this further, you can see MnO4, right? K2MnO4. So this MnO4, when you treat it with excess of what is that? Acid. When you are treating it with excess of acid, it gives disproportionate reaction. Means what? Disproportion means what? The particular now MnO4, okay, MnO4 minus 2, this gets split. Disproportion means what? It gets splits into two further compound, that is MnO4 minus and MnO2. Okay, so MnO4 minus and MnO2. So it gets disproportionate. So MnO4 minus, further when it is acidified, it gives you potassium permanganate. Okay, that is KMNO4. So you can see the commercial preparation MnO2 when it is fused with KOH, or with air, or that is when it is oxidized with air or KNO3, it gives you manganate ion. This manganate ion further undergoes electrolytic oxidation, or it is said that disproportionate reaction, to give you permanganate ion, which is purple in color. Okay, so your transition elements, they are very important reactions, and these transition metals, they play with the color. Okay, you have seen the previous preparation also. First it would give yellow color, then it is converted into orange crystals, right? Here also, when you are preparing potassium permanganate, first it forms a green color, dark green color solution. Further, when it is treated with acid, when it is acidified, it is converted into a purple color solution. So manganate ion, first the magnet ion, it will be green color. When it is converted to permanganate ion, then it will be purple in color. So transition elements, they are what you can say, they play with the color. Okay. So this is the preparation. Okay. So first, in the first step, what is produced? Manganate ion is produced, and in the second, permanganate ion is produced. Okay, so this is the, can you tell me what is the oxidation state of KMnO4 Mn? Yes, can anyone? Okay, Jyoti has answered it as 4. Others? Jyoti has answered it as 4. Okay, again she has answered it as 8. Komal has answered it as 7. Others? Plus 1 plus x minus 8 is equals to 0. X is equals to x minus 7 is equals to 0. X is equals to 7. So it is 7. Okay, so potassium permanganate, it will be 7. So just see, potassium is plus 1, Mn is x plus 4 into minus 2 equals to 0. Each oxygen is minus 2. There are 4 oxygen atoms. So plus 1 plus x minus 4 to the 8. So it will be minus 8 is equals to 0. So x is equals to, so minus 8 and plus 1, it will become minus 7 equals to 0. So when you take the 7 that side, it becomes plus. So x is equals to 7. Okay, so potassium permanganate, the oxidation state of Mn will be plus 7. Okay. Now, what are the properties of KMnO4? So, potassium permanganate. Okay. So, this is also, it acts, it is a good oxidizing agent. Okay. So, it oxidizes. So, it is acidified. So, KMnO4, it acts as a good oxidizing agent. Then, so it acts as a good oxidizing agent in various type of reactions. Okay. So next we'll see what is the structure. So there are various reactions. So various reactions are not so important. So next we'll see the structure. So what is the structure of potassium permanganate? So the permanganate, so manganate structure first we'll see MnO minus. Okay, this will be double O and O. So this is a tetrahedral structure. This is a tetrahedral and this is a manganate. Manganate, this is a green color ion. Okay, the first reaction. Manganate ion. Then permanganate. Okay, so this is tetrahedral. So this is permanganate. Permanganate, that is purple ion. Right. So permanganate, it is a purple ion. So this is the structure of permanganate. So this is a manganate ion. This is a permanganate ion. So the MnO4 minus. So MnO4 minus. Okay. So yes, both the structures are tetrahedral structures only. Right. Only what you can see here, this is MnO4. Okay. This is MnO4 minus 2. And this is MnO4 minus. Right. So this is a manganate ion, MnO4 2 minus, and this is MnO4 minus. Both are tetrahedral structure. So the MnO4 2 minus, this is paramagnetic. This is paramagnetic. This is paramagnetic with one unpaired electron. Okay, it has one unpaired electron, but MnO4, okay, MnO4 minus, it is diamagnetic. This is diamagnetic. Okay, here the pi bonding takes place by overlap of p orbitals of oxygen with d orbitals of Mn. So why it is diamagnetic? Because the pi bonding which takes place between the overlapping of p orbitals of oxygen with the d orbitals of Mn. Okay, so these are the main two structures of this. Okay, this is Mn, that is manganate ion. This is permanganate ion. Understood? Any doubts? So the properties, KMnO4, it acts as a strong oxidizing agent. In the presence of dilute sulfuric acid, KMnO4 is reduced to manganese salt. Okay, that is MnO4 minus plus 8 H plus 5 electrons gives you Mn2 plus Mn2 plus. Okay, Mn2 plus means this 2 plus will be down. Mn2 plus. Yeah. So Mn2 plus. So it is converted from MnO4 minus. Okay, that is so from KMnO4, that is from plus 7, it is converted to plus 2. So giving you the manganese salt. So acidic KMnO4 solution oxidizes. So acidic KMnO4 solution, it oxidizes oxalates to carbon dioxide, iron 2 and iron 3, nitrites to nitrates and iodides to iodide. These half reactions of reductants are. So these are some of the properties of KMnO4. Okay, so these are some of the reactions where it is acting as a good oxidizing agent. So to acidify KMnO4, only H2SO4 is used and not HCl or HNO3, because HCl reacts with KMnO4 and produce Cl2, while nitric acid itself acts as oxidizing agent. Okay, so whenever you want to acidify the KMnO4, we are making use of only sulfuric acid and we are not making use of other acids like HCl and nitric acid. Because if you react with HCl, then KMnO4 will react with HCl and it will produce chlorine gas. Okay, while HNO3, when we are talking about HNO3, it itself is a oxidizing agent, right? Then in alkaline medium, KMnO4 is reduced to insoluble MnO2. Okay, it is MnO2. So your MnO4 minus plus 3 electrons plus 2 water give you MnO2 plus 4. So in alkaline medium, it is acting as a it is reduced to insoluble MnO2. So alkaline or neutral KMnO4 solution, it oxidizes I minus to I, O3 minus, then H2O3 2 minus 2, SO4 2 minus, Mn plus 2 to MnO2, etc. So what are the other uses of KMnO4? It is acting in the for the preparation of chlorine gas. Okay, in the laboratory we are making use of. Then it is acting as a good oxidizing agent, and it is acting as a disinfectant. Then it is used in the making of Bayer's reagent. So these are some of the important properties of KMnO4. Clear? Any doubts? Any doubts in D block elements? So next we are going to start with F block elements. So any doubts in D block elements? Yes? Any doubts? Okay. So we'll start with the F block elements now. So next is F block elements. So what are F block elements? So F block elements, they consist of two series. The two series are lanthanoid series and actinoid series. So F block elements, they are called as the inner transition elements. They are called as what? They are called as inner transition elements. They are called as what? They are called as inner transition elements. So they consist of two blocks, that is F block elements, that is lanthanoid series and actinoid series. So these lanthanoid series, they are called as rare earth metals. Okay. So lanthanoid series, they are known as rare earth metals, and actinoid series are known as radioactive elements. So they are from thorium to lawrencium. Okay. Then what are the general characteristics? So the general configuration is xenon 4F. Okay, that is 4F to 1 to 14, NS that is 3D 0 to 1, and that is 6S2. So or else I can give you the general electronic configuration. So in this elements, the F block, F orbitals. Okay, here what is happening? F orbitals of the ultimate shell, it will be gradually filled with electrons. So therefore, the general electronic configuration will be N minus 2 F 1 to 14. Okay, then N minus 1 D 0 to 1, then N minus 1 1 to 2. More generally, okay, if I give you most generally, then this will be the general electronic configuration. So it consists of which two series? Lanthanoids, okay, the 14 elements following the lanthanum, and actinoids, the 14 elements which are followed by actinum. Okay, so these are the two series, lanthanoids and actinoids. Okay, so the lanthanoids are known as rare earth metals and actinoids are known as radioactive elements. Okay, then so we'll go for the, they give, so if we consider the lanthanoids, okay, so lanthanoids, so there are 14. Okay, so the lanthanoids, first we'll start with the lanthanoids. So the lanthanoids, okay. So the elements which are there in lanthanoids are, first is lanthanum. Okay, I'll write the short names: lanthanum, then cerium. Okay, cerium, then praseodymium, that is Pr, then neodymium, that is Nd, then promethium, that is Pm, then samarium, that is Sm, then europium, that is Eu. Okay, then gadolinium, that is Gd. Okay, then is terbium, that is Tb. Then next is dysprosium. Dysprosium is Dy. Then holmium. Holmium is Ho. Then erbium is Er. Next is thulium, that is Tm. Then ytterbium. Okay, ytterbium is Yp. And next is lutetium, that is Lu. So these are the elements under lanthanoids. So La, it is 57. So cerium 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, and 71. So these are the elements which come under lanthanoids. Okay. So if I write for lanthanum, I'll write it for first and last. You can write it in between. So this will be xenon 5D1 6S2. Okay. And when I'm writing for lutetium, it will be xenon 4F14, okay, then 5D1 and 6S2. So these are the what you can say general electronic configuration. You can write for the others in between. Okay, lanthanum, and last is lutetium. Okay, lutetium. So these are the elements which come under lanthanoids. Okay, now we'll see what are the properties. So what are the properties? General electronic configuration. Okay, we have seen the general electronic configuration. So general electronic range, configuration is xenon 4F1 to 14. Okay, 5D 0 to 1 and 6S2. So this is what? This is about lanthanoids. So this is the general electronic configuration of lanthanoids. The previous for F orbital, it was N minus 2. N minus 2 F 1 to 14, then N minus 1 D 0 to 1 and NS 1 to 2. This is for F block. This is for F block element, the general electronic configuration. This is for lanthanoids. So for lanthanoids, it is what? Okay, xenon 4F 1 to 14, 5D 0 to 1 and 6S2. Now, so this is very important. The next is atomic size. Atomic and ionic size from left to right decreases due to increase in nuclear charge. So this is called as lanthanide contraction. So atomic and ionic radii of lanthanoids, what happens? They gradually decreases. They gradually decreases from lanthanum to lutetium. Okay. So this gradual decrease in the size, it is called as lanthanoid contraction. Okay, and why? What is the reason? It is due to poor shielding of one 4F electron by other in the second inner shell. So this is the reason why it is showing lanthanide contraction. So it is due to poor shielding. Why? It is due to poor shielding. It is due to poor shielding of one 4F electron by other in the second inner shell. So automatically, that is from atomic and ionic size, okay, from left to right, it decreases gradually. Okay, why? It is due to poor shielding of 1F 4F electron by another and in the second inner shell. So this is the reason. Very important. These two points are very important. First, the general electronic configuration of lanthanoids, and the second one is what? Second is the what is the reason for lanthanide contraction. Then consequences of lanthanide contraction. The element of 5D series have almost similar radii as compared to 4D series. When you are talking about 5D series and 4D series, okay. So 5D series means what? It will come to the next period, okay. 4D. So when you are talking about the size, okay, when you're talking about the radii, so the elements of 5D series will have same radii as compared to that of 4D series. For example, zirconium. For example, the zirconium, okay, zirconium metal, that is Zr, will have 160 picometer, and the element in 4D series, that is hafnium, is also having 159 picometer. Okay, so these are the consequences. Means the so some of the elements in the 4D as well as 5D, they are showing same size. Why? It is due to poor shielding. Okay, it is due to poor shielding. So almost the size of zirconium and hafnium is similar. Now another reason, due to lanthanide contraction, the elements of 5D and 4D series occur together in nature. Hence, they are difficult to separate. So because of the same size, these elements which are present in 5D series and 4D series, they are occurring in nature together. Okay, so it is very difficult for their separation. So these are the two consequences of lanthanide contraction. So first is what? The some of the elements in 4D and 5D, they are having similar size. Okay, so They are having almost same radii. Second is what? Due to this lanthanoid contraction, the elements which are of 4D and 5D series, they are exhibiting together in the nature. Hence, it is very difficult to separate. So these are the two consequences of lanthanoid series. Next is, this is given as all the lanthanoids are silvery white soft metals and they tarnish rapidly in air. So these are silvery white soft metals, but when they are exposed to air, they get tarnished. Okay, they get tarnished. Then many trivalent lanthanoids ions, they are colored. Okay, both in solid state as well as in aqueous state. Neither lanthanum, neither lanthanum nor lutetium shows any color, but the rest do so. The first element and the last element of the lanthanides, they do not show any color, but in between all the other elements they show colored. Okay, so they show color in both in solid state as well as in the aqueous state. Fine. Then lanthanoids are very reactive metals like alkaline earth metals. You know alkaline earth metals, right? So like alkaline earth metal, lanthanides are also very reactive metals. Okay, so these are some of the general characteristics. So lanthanide methods, lanthanide metal. Okay, if I take any metal, then if it reacts with oxygen, it forms M2O3 oxides. It forms lanthanide oxides, that is M2O3 in the form of M2O3. Then lanthanide metal, when it reacts with N2, okay, that is nitrogen, it forms Mn, because lanthanide will be in the plus 3 state. Commonly oxidation state of lanthanide is plus 3. Then when it reacts with sulfur, it forms M2S3. Okay, it forms M2S3. When lanthanide, it reacts with carbon, it forms MC2. Okay, then when it reacts with halide, it forms MX3. When it reacts with water, it forms hydroxides like MOH thrice plus H2. Okay, so these are some of the reactions of lanthanide metals. Then misch metals contains lanthanoids about 90 to 95%. Okay, so cerium, that is 40 to 5%. Okay, 40 to 45%. Lanthanum and neodymium 44%. Iron 4.5%. Then calcium, carbon and silicon used in cigarette and gas lighters, toys, tank and tracer bullets. So these are some of the important, you can say, lanthanoids where it is used. So misch metals is nothing but it is said to be alloy. Okay, it is alloy of some rare earth elements. So for example, from cerium, so it may consist of more of cerium misch metal or some any other rare earth. So typically composition, it includes more of cerium. So whenever cerium alloys are made, so they are called as misch metals and they consist mostly of cerium. So 40 to 45% consists of cerium, then lanthanum, then you can say some neodymium and some traces of some other rare metals are obtained. So these misch metals are very important. So they are used in cigarettes, then in gas lighters, toys. Okay. So these are some of the uses of misch metals. Then about oxidation state, when we are talking about oxidation state, okay, when we are talking about oxidation state of lanthanides, the most common oxidation state of lanthanide is plus 3. As I have discussed, the most common oxidation state, very important, oxidation state is very important. So when you are talking about oxidation state, the most common oxidation state of lanthanides is plus 3. However, it shows plus 2, plus 4 are also shown by some of the ions. So plus 2 and plus 4 oxidation state also are shown by some of the ions in aqueous solution form or in the solid compound. Then the irregularity. So this irregularity is due to extra stability of empty or half filled or completely filled subshell. So the irregularity shown, okay, in the oxidation state is due to the extra stability of half empty or half filled or completely filled f orbitals. So the +4 oxidation state of cerium. So cerium, it shows +4 oxidation state of the cerium is due to the noble gas configuration. So cerium, it shows +4 oxidation state. Why it shows +4 oxidation state? It is due to completely filled noble gas configuration. But it is a strong oxidant and hence easily undergo reduction to form +3 state. So cerium, it mostly forms +4 oxidation state due to the noble gas configuration, but it is a good oxidant and hence it can easily undergo reduction soon and it forms +3 also. The elements like Pr, okay, then Nd, then Tb and Dy. Okay, so we have seen this. So they also exhibit +4 oxidation state, but only in the oxides, but only in the oxide forms. Only in the oxide forms, they form +4 oxidation state. Similarly, ytterbium, that is Yb+2, and it has, so similarly this Yb+2, it is a strong oxidant and changes to +3. So this also shows +4 oxidation state. So it is a good oxidant, but it will get reduced sooner and it will show +3 oxidation state. Okay, so these are some of the important properties. So these are some of the important properties of lanthanoids. Okay, so we'll see some of the general characteristic. Is it clear till here, whatever we have discussed? Yes. Is it clear? Okay. So next are the general, what you can say, general properties. So I'll tell you in short, not so important, general properties. So general properties, physical properties, as we have discussed, these are silvery white. They are soft metals. They get tarnished easily in air. They melt at very high temperature. They are good conductors of heat and electricity. As they are metals, so they will have a good properties of metal. What the good metal will show, the same properties will be shown by the metal. So they are good conductors of heat and electricity. Their hardness increases with the increase in the atomic number. Why? As you go down the group, what will happen? The size increases. So because of that, the hardness also will increase. Okay. So these are the physical properties. Next is they form colored compounds. So trivalent lanthanoids. Okay, they are ions are colored in solid state as well as aqueous state. So we have discussed this also. So the trivalent lanthanoids. Okay, trivalent lanthanoid means what? The elements when they exist in +3 oxidation state. So they will show color form in aqueous state as well as in solid state. Then only the lanthanum. So the first element that is lanthanum and the last element that is lutetium. Okay. So these only are colorless. These both are colorless while the other elements in between all are colored. Okay. So they are all colored and it is due to why they are colored, because it is due to the presence of unpaired f electrons. Okay. It is due to the why the other elements, so most of the lanthanums ions are colored. It is due to what? It is due to presence of unpaired ff electrons. Okay, that is ff transition. It is due to unpaired ff transition. Understood? Then next point, the lanthanoids ions other than okay, that is lanthanum and cerium, while the others all are paramagnetic. Okay, so the lanthanum ions other than this La+2 and La+3 and cerium+4, the elements which are having +14, that is which is having +4 oxidation state. So all are paramagnetic in nature. So these are all paramagnetic in nature. Then we have seen the reactions. So these are the chemical properties. So lanthanide metal, when it reacts with, when it is burned with oxygen, it forms M2O3 type, M2O3 type of oxides. when it is reacted with N2. Okay, when it is reacted with N2, it will when it is it forms Mn, that is nitrites are formed. Then when it is reacted with sulfur, what is formed? It is when it is heated with sulfur, it forms M2S3. Then lanthanoid metal, when it is reacted with carbon, okay, when it is reacted with carbon, the temperature is given as 2773 Kelvin. So it forms Ln, that is Mc2 type. Then lanthanide metal, when it is reacted with halides, it forms MX3, that is halides, respective halides are forms. Then when it is reacted with water, it forms hydroxides. So these are some of the properties, chemical properties, how the reaction takes place of lanthanoids. Then what are the uses of lanthanoids? It is in the production of alloy steels, like for example, mish metals. Okay, mish metals means what? It is made up of lanthanoid metal. So about 90 to 95% of cerium is there. Okay, plus iron is there. Then traces of sulfur, carbon, calcium, and aluminium are produced. Then where it is used to produce this bullet shells. Okay, shell of the bullets and lighter. Okay, lighter flint. So these are mish metals are also very important. So lanthanides only produces this mish metal. So these are type of alloy steels. Okay. Then next point is mixed oxides of lanthanoids are used as catalyst in petroleum crackling. Okay, so in petroleum crackling, the mixed oxides of lanthanamide use. Then some of the lanthanide oxides are used as phosphorus. Okay, phosphorus in TV screens and fluorescent in fluorescing surfaces. So these are some of the uses of lanthanoids. Is it clear? Yes. So these were some of the uses. So mish metals, very important. So this use is very important, mish metals. Okay. So mish metals is very important. Uh, so, so we have completed the lanthanoids. So in the next class, we will see about actinides. Any doubts about lanthanoids? Yes. Okay. Okay then. So if there are no doubts, so we can proceed about actinoids in the next class. Okay. So please just go through the lanthanoids. If you have any doubts, you can ask me in the next session also. Okay. So I'll end the class here. So we'll meet in the next class. Okay. Thank you.